Alright, enough of the theory. Back to the coding, what we all love. So now's the time to implement a bit of that theory. I'm going to change app.hpp. This hasn't changed since we last worked on it in the last lesson. First thing I'm going to do is include our clock because we'll need that later. And then I'm going to add a few private member variables to our CApp class, and these are them here. A float called angle, and this is just going to hold the rotational angle when we rotate our triangle. I'll explain later. And you recognise these things. We've got the world matrix, the view matrix and the projection matrix, what we were just talking about. And Direct3d has a structure here which will hold matrices for us, and that's just D3dx matrix. So I'm creating 3 D3dx matrices: world matrix, view matrix and projection matrix. These are three-dimensional vectors, mathematical vectors, points in space or directions in space, and this is the I vec, the look vec and the up vec, and I'm just I'm going to explain what these are when we start to use them, when we implement some more of our CApp class. And I also want to add a new public method, and this is called update. This is going to be called once per frame, and it's going to update any of our logic and variables and all that kind of stuff. It's going to return handle to result like the initialize and the render methods do, and we're also going to pass it as argument float dt. Now you might recognise this. We're actually going to pass the update method, the output from the update method in our clock, and that is everything. That's all we're going to do in app.hpp. And now to the real main part of the lesson. We're going to change app.cpp to start animating movements in our triangle. The first thing that I want to change is this vertex struct, because if you remember in the second lesson we declared this RHW float here, and this signifies that we're in screen space, because in lesson 2 we were working in screen space. But in this lesson we're going to be working in the four spaces: modelling, world, view and screen. And so we're not going to be just working in screen space anymore, so we don't need that anymore. We don't need to signify that we are, because we're not. And then we're also going to change our flexible vertex format, because if you remember, this declared the type, the structure or the format of our data, of our vertices, sorry. And we're not working in screen space anymore, so I'm going to delete the RHW, so we're left with just Direct3d flexible vertex format XYZ. The third change is how we declare our vertices. Now we have changed this struct. We only have X, Y, Z and colour now, so obviously this is going to get compile errors all over the place, because we don't have this anymore, which we used to be our RHW. So I'm just going to paste in how we're going to declare our vertices. Just comment these out so we can show our changes. You notice we've got rid of the ones to signify we're in screen space. They've just gone, and then we're left with the vertices of it, the coordinates of each vertex, and the colour of each vertex. The colours are going to stay the same, and the change to each coordinate here is to signify that we're working in modelling space. Remember what I said before? We're going to declare the centre of our model to be 0.000. So -1, -1, 0 is like down here somewhere. If we think 0, 0, 0 is in the center of the screen, yeah, -1 in the x, -1 in the y. 1 minus 1, 0 is down here somewhere, because if we start in the center of our screen, we'll go 1 and then -1. 0, 2, 0 is up here somewhere, because we're just going up 2 in the y. So those are our vertices in this triangle's modelling space. Okay. The next thing I'm going to change is just a simple one. After we have filled our vertex buffer and unlocked it, we're just going to initialize the angle to 0, because this is our initialize method after all. And we're also going to initialize the 3 member vectors that were declared in the header file, eye, look and up. And these are concerned with our camera, or our eye, it depends which way you want to look at it. The eye vector is the position of the eye in world space. So we're in the world now, just forget about the modelling space for a second. Where do we want our camera to be? And I'm going to say it's at 0, 0, -3. So center of the screen, -3 out of the screen, -3 units out of the screen. Look vector is where our camera is currently looking, so I'm going to say I'm going to look at the center of the world, 0, 0, 0, and the up vector is the direction of up. So you can think about vectors, these two are points and this is a direction, because vectors can be points and directions, and 0, 1, 0 is the arrow that points up in the y. So those are our vectors concerned with the camera. And the next thing we're going to actually do is calculate our view matrix, which passes us from world space to view space. Now we don't have to do any of the hardcore maths or anything like that. Direct3d provides us with a method called D3dx matrix look at LH, and all we're going to do is, it's incomplete, 1 second. There we go. All we're going to do is pass our eye vector, our look vector and our up vector, which are concerned with our camera. It's going to do a load of calculations, and then it's going to hook up our view matrix member variable. It's going to fill that member variable with the required matrix to calculate, to transform our vertices from modelling space, from world space to view space, because this is a view matrix that goes from world space to view space. The next thing we're going to do is calculate our projection matrix, which will take us from view space to screen space. We don't have to do the maths again. Direct3d provides us with D3dx matrix perspective FOV LH. It's going to hook up the projection matrix, going to fill the projection matrix with the values which correspond to having these 3 inputs. Now, these 3 arguments here, d3dx pi is just pi, like 3.142. Pi over 2 is radians for 45 degrees. Is it 45 degrees? Pi over 2? 90 degrees, sorry. Yeah, 90 degrees. And this is the field of view. So basically this is the zoom factor of our camera. We can control how much zoom it has got. The wider the field of view, i.e. the bigger this value, it's going to basically correspond to a zoom out in the camera.